All right, so for our second lecture this week, we're going to look at interfaces a bit more. Specifically, we're going to talk about functional interfaces and how they relate to some of the JavaFX stuff that we're going to do in the future. And we're going to talk a bit about generics as well. So to sort of start us off, I want to give sort of a real example of a useful interface. It's called comparable, and it has some generic syntax. The angle brackets that you see here are this idea of a generic, either a generic interface in this case, or a generic class, or a generic function. It's this sort of generic sort of interface stuff, this sort of generics that Java allows you to do it. And for now, at least until we get into a little bit later today, for now, just know that it's just a class name that goes in there. So this will be some class. Like if we create an array list of cards, like in the blackjack game, then you would put card in there. And so in this case, you would have a interface that allows you to compare cards, for instance. So this interface, the code for it is very simple. It's just a public interface. It gives you a couple of comments on sort of what it's meant to do, and it has one method, compare to. That's it. Because it has one method, it's what's known as a functional interface. And we'll get to that in a couple of slides. But I want to do an example with this one. And in fact, we're going to take our circle from last time, and we're going to add the comparable interface to it as well. And I'll sort of show you how these sort of angle bracket things work with the T in here, and sort of what we can do with this interface. So I'm going to go to Eclipse, and I already have a circle open. So my circle up here is already ready. It's what we coded last time, implements measurable. Now, if I want to implement another interface, I just do a comma, and then let's say we want comparable. And I need the angle brackets because that's part of what comparable is. I put a type in here. So let's put circle in here. So what this will allow me to do is compare two circles, because I'm going to have a function now. I need to implement my unimplemented methods. And it's going to give me this compare to, and it fills in circle. If we go back to the slides, notice that we put a type in, and that same T gets put in the method compare to. So it's kind of like this comparable anyway, is kind of like an equals. Remember we messed around with the sort of dot equals stuff and overriding our own equals. It's similar. It returns a negative int, a 0, or a positive int. And how we define negative, 0, or positive, that's up to us. We write the method. Comparable gives us the interface. It gives us the contract saying that compare to must exist. But what compare to is, that's up to us. That's totally up to us. So we can write whatever code we want to in here. I think in the slides I use a compare from like the double class or something, but really you could do whatever you want. In the slides I have like a double dot compare, and it just compares the radius, if I remember correctly. So it'd be like this dot radius, and O, that's the circle that comes in, dot radius. This is the circle that called compare to, and O is the circle that we're comparing to. Because remember, to call this method in my main, I would write something, pull my pen out here, I would write something like this. I would have like C1 dot compare to C2. It'd be something like this. So C2 would come in as O. And C1 is this. So that's the idea here of using this type of interface. The point that I want to make with this sort of particular example is that Java has a bunch of built-in ones that you can just use. And typically they're going to be this sort of generic style because they want to be very sort of open to use, not just in specific circumstances, but sort of in a lot of different situations. So again, we'll talk more about this generic idea a little bit later in this lecture. But there are lots and lots of these that Java provides for you. Of course, you make your own, like we did with measurable, but comparable is one of the ones that are out there. And I think one of the cool things about this one is it doesn't just return a true or false. And that's what, of course, equals does that. And so if we wanted to just return true or false, we would just use the dot equals. But this returns a negative, a zero, or a positive number. The important part about that is you can get some kind of ordering. So think about a card game, right? Think about blackjack. Which hand is better in blackjack? It's pretty easy to sort of figure out just by looking at the hands. But in code, you could have a comparison where you compare two hands. So you could use a comparable interface in the hand class to be able to easily say hand one compared to hand two. And if you get back a zero, then you would say the hands are the same, at least numerical wise. If you gave back a positive number, that would mean that one hand was better than the other, and a negative number would mean the hand was worse than the other one. So you could get this sort of ordering, this sort of natural ordering when you use a compare to, and that can be very powerful in a lot of circumstances. I've had a group in the past for their final project do basically take the sort of blackjack game and turn it into Texas Hold'em. Typically, I don't sort of allow folks to take one card game that we do in class and turn it into another one. But the difficult part about Texas Hold'em is how do you figure out which hands are better than what other hands? Now, obviously, there's set rules for it, but you have to get it working on the computer and let a computer know that certain hands are better than other hands. And you don't want to code up every single possible hand and sort of give it a number or something. That would be super tedious and not very feasible. So they used a comparable and were able to come up with an algorithm in here that would determine a negative, a zero, or a positive number. And then they could use that to order the hands in the order of how good they were. And then, of course, the one with the best hand was the one that won the hand. So there was some cool sort of algorithmic stuff that sort of went along with this compare to. And the compare to was probably their most complicated thing that group had to figure out. So there is some cool stuff that you can do with this, and it can be useful in a lot of situations. So here's that code, that little sort of compare to sort of show you how this can work. And then in main here, it sort of shows some of this as well. All right, so Java 8 does allow for a couple of extra things in your interfaces. We're probably not going to use these, or at least I'm probably not going to use these, but they are allowed. So you can have static methods in your interfaces. You wouldn't be able to override them in something that implements the interface. So think of it as kind of like a utility method, a method that will always sort of be implemented in that way. And a class that implements the interface wouldn't need to change it. Or you can have default methods. So you can give an implementation, and then maybe a class somewhere along the way would sort of redo it in a way that it needs it. So these do exist. You can use them. You can use static. You can use default. Typically, when I'm doing stuff for this class, we won't need them. But they are there in case you run into them, or in case you realize that something like this might be useful in an interface that you use in the future. All right, I mentioned a functional interface just a few moments ago, and it's just a regular interface that just has one method. That's it. So our measurable interface that we wrote last time is not a functional interface because it has two, but comparable is a functional interface. And really, you don't do anything special. You just only have one method, and it's automatically functional. And if you have more than one method, then it's not functional. So there's nothing sort of extra you have to do. A lot of interfaces already exist in Java, like I said, and there are specific functional interfaces that exist within the Java util function package. So things like a predicate or a bipredicate. These ones return a Boolean given a single parameter of type T. And remember, the T here or the T and the U here, the stuff in these this sort of generic angle bracket syntax is just a class. It's just a particular type. So it could be card and hand for the T and the U. It can be whatever you want. You're the one who decides. The thing to remember about these interfaces is that you are still the one that defines what they mean. And that's something that can take a little bit to sort of fully realize. This isn't something that's just going to work right out of the box. You give it, you implement by predicate, and then you're done. No, you have to implement the method. You have to tell it, what does it mean? How do you get true or false given 2 parameters? Or for the predicate given 1 parameter, how do you define true or false? That's up to you. Now, the benefit, what we get out of a functional interface, is what's known as a lambda expression. Or you'll probably hear me call them lambda functions or anonymous functions or anonymous expression. So if you hear lambda or anonymous related to Java, it means this. There are other languages that sort of do slightly different things with lambda functions or anonymous functions, but with Java, it specifically references functional interfaces and a way that you can use them. Lots and lots of languages have this sort of lambda expression style stuff. So most likely you will sort of run across them in other languages you use. Even something like Excel has lambda expressions. So, it's not just sort of a hardcore programming thing. These sort of things are everywhere. There's lots of various syntax things when it comes to lambdas. So what I'm going to do is I'm going to show you multiple ways to achieve the same thing with a functional interface. So we're going to do an example where we got sort of several different styles. Some of the syntax when it comes to lambdas, we'll talk about when we actually write a lambda, but a lot of things can be omitted. That's something to sort of remember here. You can omit certain parentheses. You can omit brackets. You can omit a return if there's a return value. You don't have to put the types in for the variables. So there's all sorts of stuff that you can omit to make these lambda functions very, very short and succinct. We'll talk about those when we write a lambda, but I want to show you one of these sort of things first. I want to type up just an example where we do the sort of regular stuff we've been talking about. We'll create an interface, we'll create a class that implements that interface, and we'll have a main that does something. Almost the same as our circle, rectangle, and main with our measurable interface. It'll be that same style of thing. So here in Eclipse, I'm going to close out what I have here, and I have an empty project sort of ready to go. And we're going to create 2 classes and an interface. The first class is just going to be main, and I'm going to set it up so it has a main method. And the next class is going to be a class called isEven. So kind of like asking a question. isEven. So that's going to be that one. And then we're going to create an interface. And this interface, we can sort of name it whatever we want to. I'm just going to name it capital I1, just sort of interface 1, because I don't have another sort of specific name for it. Did we? Let's see. It looks like I think it did create it. There was just something with Eclipse here. So it should, yes. So we created the file, just didn't put anything in it. Okay. So we'll put the public interface part in here. So this will be a public interface, I1. And we're going to make this a functional interface. So it's only going to have one method. Remember, in interfaces, we can omit the visibility. So I'm just going to put Boolean. And the method is going to be called test. And it's just going to take a single value called x, and that value is going to be an int. Now, the way that I've written it right now, this is a functional interface. But there's also an annotation. Remember, we used the @override previously. There's an annotation that sort of ensures that this will be a functional interface. It'll give me an error if for some reason it is not a functional interface. So it's just and then functional interface. So if this wasn't a functional interface, Let's see, spelled that wrong. F-U-N. There we go. If it wasn't a functional interface, then we would get sort of an error related to the whole thing. But it is, so everything here should work fine. And this is it for our interface. We're not going to do anything else with this file. So that's something to sort of keep in mind. Functional interfaces are very, very simple. One abstract method, and if you want to, you can throw the tag in as well. Now, my isEven, that isEven class that we created, this is going to implement I1. So of course, I need to implement that method. So here's my method. And let's do something very simple here. Let's just return, x mod 2 equals 0. So this is just a true or false thing here. This is just checking, is x mod 2, is that equal to 0? True or false? That's it. So that's all this class is going to do. The whole purpose of this class, and this is sort of the point that we're going to get to a little bit later. The whole purpose of this class is to do one thing. It's to implement the interface. So it's almost like a waste, where it's like, okay, we created this interface, and then we have to write a whole class that implements this interface just to get this one function. So if you're thinking, oh, that kind of seems kind of weird that I have to write sort of all these extra files and have this extra code in order just to implement that one test function. And that would be absolutely correct. That's where the Lambda is going to come in a little bit later. So let's go back to main. And let's write a function. Let's write a function here. So this will be public static. Yeah, we'll do void happy or sad. That's what I'm gonna name this one. And this is going to take an I1 that I'm just going to call var. So this takes something that implements I1. Right? We did that for our measurable, right? We had the function that took a measurable, and we could send in a circle or a rectangle to that function. This is the same type of thing. So what we're going to do is we're gonna print out some stuff. We're going to print out the numbers 0 to 9. So I'm going to have a for loop starting at 0, going to less than 10, and doing I++. And we're going to print out the number. So we're going to have system out printf. And I'm going to print the %d. And I'm going to put a colon. And I think that'll probably be good for that. So a space and a colon, and then we're going to print out that d is going to be I. So we're just going to print out the numbers 0 to 9. Now that's going to happen. So we're going to print out 0, and then we're going to do a little test. So we're going to say if var, that's my class that implements interface, dot test, because test is the method that's guaranteed. It's in our contract. It's guaranteed to be part of var. We're going to test that number I. We're going to call test on that number I. If this comes back as being true, then we're going to print a closed parenthesis. And we don't have any arguments or anything in here. Otherwise, we're going to print an open parenthesis. This. And then at the very end, after the for loop, so our for loop closes there, then we'll print a new line. So you're going to see what this does in a second, but just keep in mind, if you're printing out 0 through 9, we could probably print out 0 through 10 if we wanted to. But we're going to print out 0 through 9, print out 2 I's, and then either happy or unhappy, depending on whatever this test gives us, true or false. Because remember, it gives us back a Boolean, true or false. So I can use it directly in here to get true to print out the smiley part, or false to print out the sad part. So let's create a new isEven. So I'm going to create an isEven object that I'm just going to call IE. This is a new is even. And then we're going to send it in. Happy or sad, and we're going to send in IE. This is exactly the same as when we had the measurable function and we sent in a circle. So I'm sending in an is even. We know already that is even implements I1, so this function is guaranteed to exist. So that's what comes in here. So var is our is even. It has the test, and we're going to run it. We're going to run the test and decide what to print based on that. And it looks like, did we not get our new line right here? Let's check. Make sure this is saved. Ah, yes. Not outside the for loop, inside the for loop after our if. That's where we want the new line. So there we go. So that test would look at the number and determine if it was even or odd. If it was even, we would get back a true. So all of the even numbers have the happy face. And all the odd numbers have the sad face. Now I'm going to show you 3 other ways to do this exact same thing. Keep in mind that there is some polymorphism happening here because we're sending in an is even as a I1 and treating it like an I1. But like I said before, the entire purpose of this class is just to implement I1. That's it. So like I said, it does seem kind of like a waste. We have this functional interface. We got to write a whole brand new class just to use that function, just to use this test function. I got to write a whole brand new class, create an object of that class, and send that object in. So this is where Lambda functions come in. I'm not going to bother creating the is even. And I'm going to write this in first, and then I'm going to explain it. I'm going to write x, a dash, greater than. So I basically just made an arrow. And then I'm going to do an x mod 2 equals 0. And I'm going to run the code. We get the exact same thing. In fact, this x that I put in doesn't even have to be x. Let's put in a p instead. Everything still works. Now, this very possibly, so if you sort of look at this sort of critically, this could very possibly sort of break your sort of coding sense. It'd be like, why? What is p? What does that even mean? Why don't you have to have x in there? Where's the parentheses? There's not even a semicolon. And all of it is going into this as a function call into something that's an I1. The previous version hopefully at least made sense, that we created a new object and we sent that object into something that needs an I1. Hopefully that at least sort of made sense intuitively mostly. This may not make sense at all. So really what's happening here is this. We are defining what that function in the functional interface contains. That's what this is. This is the definition of that function. And if we look at is even, I did a return of x mod 2 equals 0. That's this piece right here. The arrow part of this specifically represents that I'm writing a lambda function. So that's sort of your lambda syntax. And the first value here, the p, or like what I had before, the x, is saying what is the input value. Right? In my interface here, the input is one int. So Java immediately knows, hey, this is going to be that int. This is what that int has. And then this is the rest of the function. Now, because this function is so simple, we can omit a lot of things. And I said you can omit a whole bunch of things, like a bunch of brackets and parentheses and all that kind of stuff, which we can actually put them in. So I can actually make this a little bit more explicit. This would be the type, the variable that comes in. If you only have one variable, so like our interface here, we only have one parameter, then you can omit them. If you have more than one, like this, then you have to have it in there. You have to have the parentheses. But you can omit it. I don't need the type. I don't need to say int x. You can, but Java already knows it's an int because this is the only function that exists in the interface. So Java already knows it's an int. So you don't need to put the type. You don't need to put brackets around this, but you can. And if you put brackets, then you have to put more of the syntax. So then I have to have a semicolon, and I have to say return. So this is sort of closer to syntax that you might be used to. Yes, it's putting it just on one line, but it's a little bit closer. It's saying, here's our parameter. This is a lambda, so here's the definition of that function. And so now this looks a lot closer to what we had in isEven. But because we only had one parameter and there was only one line and that line was a return, we could get rid of a whole bunch of other syntax. So don't be scared when you sort of see some of the syntax is sort of missing. You could definitely put it back in if it's a little bit confusing. But the power here is that I bypass the entire need for this class. I don't need this class. I could delete the file. Everything would be just fine because I just defined what that interface function looks like right here instead. So whenever I call var, so this is what's going in as var. That function goes in as var. Whenever I call var.test, it runs this code. So that's why everything still works. If I say change this to 3, for example, so x mod 3 equals 0 gives us a true, then, did I say that? Yes. So here's our 0 is happy face, 3, 6, and 9 are happy face. The rest are frowny face. So that lets me easily change what the function does without having to create another class. I don't have to go in and create another class that sort of is divisible by 3 and then write this whole thing and then use that one, create a new object of that, put that in. I can just change the function right here and don't have to worry about any sort of extra classes or anything. That's the power that Lambda functions give us. Now, there are two other ways to do this, one of which is a way that I would recommend you not using. And which is one of the ways we're going to do next. And then the last way I'm going to show you is a way that it might make more sense than a Lambda function. And it's a perfectly reasonable thing to do, and you will see me using it during class as well. So let me go back to having an isEven. But we're going to, let's actually delete this isEven file. I don't even want this anymore. We'll delete it. We're not using it here. I'm just going to get rid of it. We're going to make what's known as a class within a class. So within my main class here, I'm going to make a private static class. And I'm going to call this class isEven. And it implements I1. So now I literally have a class within another class. But it's a private class, so it can only be used inside of my main class here. And I'm going to implement I1, so I need to create the test method here, and we're going to do a return p mod 2 equals 0, or x mod 2. X mod 2 equals 0. And then for our happy or sad function, I'm going to get rid of the lambda. And I'm going to do the same thing we had before. We're going to have isEven, IE equals new isEven. And then we're going to send IE into here. And this will work the same way as well as the previous two versions. This doesn't save us a whole lot. We're still ending up writing a class solely for the purpose of implementing test, this function. But it makes it so we can have one less file. I don't recommend this version. I find this to be too clunky. And having to keep track of private classes that you have within other classes is a gigantic pain in the ass. So my recommendation is not to use this way. Use the lambda that we just saw, or the next one I'm about to show you. So I'm going to delete this private class. I don't want to use it. I don't want to keep track of it. I don't care about it. We're going to do something inside of happy or sad function call again. And it's going to break one of the rules that I've told you about sort of abstract classes or interfaces in general. Interfaces are also abstract. I'm going to say new I1 and some parentheses like that. This is an error right now. It says cannot instantiate the type I1 because it's an interface. I can't create a concrete object out of it. But what I can do, and this is what I recommend when you sort of outline some of this stuff, is create an open and close parenthesis after that. Notice how the color even changed here. Before I had it, it was the bluish. And then after, it turned to this green. So there's definitely something going on. And then typically what I do is I give myself a couple returns like this. I create a little bit of space. The function call, happy or sad, still ends right here. So this is still all one line. But I have a little bit of space so I can sort of see what's going on. Now if I hover over I1, it says the type new I1 must implement the inherited abstract method test. And it says add unimplemented methods. So let's do it. I have test. Now test is here. And then I can put in what I want. I can say return x mod 2 equals 0. And I can run the code. And it gives me the exact same result that we got the previous 3 times. This is what's known as an anonymous class. This right here, the new I1 with the parentheses and then the open close bracket, that's an anonymous class. It's a class that we didn't give a name, right? The previous 2 times we wrote a class, the private class and just the actual regular class we put in a file, that was a class that we gave a name, is even. This one, we're sort of creating a class, but we're not naming it. We're just implementing this one function. So this, or the lambda, is what you'll see me use. I think this one is more explicit about what is happening. So if you're not comfortable with how lambdas work and why you can do all of this omitting stuff, omitting any of the parentheses and the brackets and the return and the semicolons, if you're sort of not comfortable with that at the moment, then this is the way to go. Because this still includes all that stuff. It still includes the override and the function signature and all the syntax. It just sort of breaks our rule of writing new and then an interface. But we give the interface a definition. We give the function a definition. Now, keep in mind, when you write a lambda or when you write an anonymous function, you want to make sure it's a functional interface. So it's going to look something like this. One abstract function. All right, so I know there was potentially a lot to take in, and especially with some of the new syntax stuff. We are going to use this extensively, either the lambda or the anonymous class part, because this is how we actually get interaction into our JavaFX programs. We will use anonymous classes, probably most often anonymous classes, but I'll put some lambdas in there as well to show you the usage for both of them. So we will be using these in the future. All right, so back to the slides. The syntax stuff I sort of talked about. Here is those pieces of code. So the one where we started with a class, went to a lambda, and a couple pop-ups here, went to a private class within a class, and then went to the anonymous class. So we have sort of all those pieces in there. So that all that code is there for you to potentially mess around with again in the future. All right, so one of the questions that you might be thinking of is, well, why use an interface over an abstract class? So obviously the sort of one of the answers to this is something we talked a little bit about last time, that you can only have single inheritance. You can't have more than one parent class. So because of that, abstract classes should be used for strong ISA relationships. And you'll hear me sort of say this sort of is a thing in the future, and I'll try to sort of emphasize it when I'm talking about certain things. For example, an employee is a person. Or if you want to think about certain types of sort of other strong relationships, a cat is a animal. Those sorts of strong relationships. Interfaces you use for weaker relationships. Oftentimes, you will associate the sort of two-word thing, has a. So maybe some car has a engine, or a cat has hairballs. So typically, it's reserved for has a style relationships, or sort of has the ability to do something, and that sort of comes into the names. So like we saw, our original sort of interface example was drawable and rows. Well, rows and drawable are not this strong relationship. A rose is a flower, or a rose is a plant. But a rose has the ability to be drawn. And so by implementing drawable, that's just one of the things that it can do. So it's not that strong sort of coupled relationship. It's a weaker one. As I mentioned a few times, interfaces do define a type. So they are used to get you polymorphism, just like inheritance is. So you can still get that polymorphism benefits from using interfaces in addition to using inheritance. So I want you to keep that in mind. I'll try to emphasize it when when I'm sort of explaining some of this stuff. This sort of is a relationship, and more of sort of a has a or can relationship, like a has a relationship, or sort of a can do something relationship. So like I said, a car has an engine. A car can move, but a car is not an engine. You wouldn't say car is an engine. So think of them sort of like that. Try to think of strong versus these sort of weak relationships. So take-home points for interfaces. They express contracts, just like an abstract class. If you implement an interface, you must have the methods that interface contains. Because of single inheritance, interfaces are used for those weaker relationships, and functional interfaces only have one method, and they provide support for those lambda expressions that you just saw, and we will see a lot more of those coming up in the future. All right, I want to talk about generics as well. This is sort of the last piece of today. So I want to talk about generics. Generics enable your type to be defined when you create the class. This works for classes, this works for interfaces, and this actually works for methods as well. So the goal here is to reuse code. If I write a generic function, that could let me use it in more situations than if I had a very specific function with specific, say, return values or specific parameters. So let me show you a little bit of a motivation. Back to comparable. So we talked about comparable. We messed around with it a little bit. The point of comparable being a generic is that I can put anything I want in T. If I couldn't do this, if I couldn't do the generic thing, then I'd have a couple options. I could have it so this is, instead of the particular type that I put in the angle brackets here, this could be object. And you've seen something do that before. Dot equals does that. And so I have to use some extra code. I have to test an instance of, and then I have to do a cast to make sure that works. Or I could make a comparable for every single type of object, which is not something that's feasible. So that's what we have. We only have a few options. This generic gives us the ability to create something that anybody can use for any purpose without having to use any of that instance of stuff. So the author of comparable, whoever that was when they were first writing some of this code for Java, they allowed us to explicitly specialize that interface for whatever we wanted it to do. They didn't lock us into object, which would work, but would mean a little bit more work for us. So to get a sense why this is useful, let's look at a previous version of Java and what you would have to do. So I mentioned that object thing. That's what it was like back in, say, JDK4. It was object. This is what the interface was. If you wrote the code down here at the bottom, this is meant to be a date. A date as in, actual day, month, year, or whatever. If I did compare to, and I compared it to, say, a string, well, a string and a date are definitely not the same thing. This would cause a problem at a different time than the Java 8 version. So Java 8, I define what the compare to is. So I say, hey, this is going to be a date compare to. And if I try to compare that to a string, the error here is going to happen at a different time than it does for JDK4. We don't get the error here until we run the program. Java sees this and goes, oh, it looks fine to me. And then when it runs, then it realizes, hey, a date is not a string. Whereas here, Java is going to tell you right away, hey, you said this was a date and you're trying to compare to a string. That doesn't work. So what happens at compile time? So one of the benefits, it's probably a less important benefit than allowing you to explicitly specialize your interface. But one of the additional benefits is that if you make some sort of error in using it, you're going to know right away, rather than waiting to have to run your program and then getting something that potentially is going to crash when your program runs. So the old style implementation would sort of say something like this. It would say, exception in thread main, and it would say class cast exception because it would try to do a cast and it wouldn't be able to, and so then you get the error sort of at that line. So that's what you would see in the sort of the old style of how Java did this. And we can actually see some of this even in sort of today's version. So let's go back to Eclipse, and I'm just going to code this little piece up. And this uses an array list, but I don't use the generic syntax. So I'm going to show you what happens when we do that. I think I have a class. Yeah, I got a quick project here. So I'm just going to make a quick main class with the method, with the main method, and we're just going to mess around a little bit. So let's create an array list. And I don't remember what I called it. So array list, call it A, and this is going to be a new array list. So nothing fancy, but I don't use that generic syntax. We need to make sure to import array list. And it gives us a warning. It doesn't stop us from doing this, but it does give a warning. And the warning says, array list is a raw type. References to generic type array list should be parameterized. So this is telling me, hey, you should put something in the angle brackets here. But I don't have to do that. It's just a warning. I can just ignore it and sort of see what happens. So if I try to take my array list and I try to add, say, some element that's a string, and then I try to add, say, a number as well. I'm going to get warnings all over the place because it's going to tell me, hey, you should use those angle brackets so I know what's going on. So it gives you a bunch of warnings. So you're probably not going to ever sort of do this, but if I run it, it seems to work. Sweet. I have an array list. I added a string and a number. Awesome. But what happens when I use it? So let's say I do something like this. I say, okay, maybe I sort of assuming my array list is a string. Well, I can't directly do this. I can't say a.get0. This is going to give me the first element. I can't actually do that because this just thinks it's an object. So that's actually what's happening here. This is equivalent to me putting object in here. Well, if I'm trying to get a string out of this, then I have to do a cast to a string. This. And if I try to do that for the next element, like this, well, I know that's a 5, but of course, if you're in some gigantic program, you may not know what this is. We start to run into problems. Oh, this should be S2. It doesn't catch it right here. It only catches it when I run the program. Because now it actually checks, hey, wait a second, this is an integer. You're trying to cast it to a string. That ain't going to work. So the results of sort of ignoring this sort of style here of using the generics means that you're going to be running the program to check and see if stuff is working. Whereas if I explicitly put in, so let me do this, we put in string here, and I'll put it in over here as well. Whereas if I actually put the generic in, what I want this to be, an array list of strings, then I immediately get an error here that says, hey, you're trying to put an int in, and it should be a string. And so then I don't have the problem when I try to run anymore, because I've gotten it at compile time, not at runtime. So that's something that generics get us. It helps us find errors sooner, which is always useful. All right, so I show what some of these sort of issues are here, and some of the stuff that it sort of shows when you start trying to mess around with this stuff. So that's the idea here with these generics. They give you not only the ability to specialize a particular class or a particular method or a particular interface, but they also give you the error that might crop up sooner. All right, so when you use generics, use the angle brackets. So like array lists, it's meant to be generic. A comparable is meant to be generic. And then put in whatever type you want for that array list to be, or for that comparable to represent. So again, the biggest thing here, generalizable code. Write it once, use it for any situation, or many situations. While at the same time, you get fewer runtime errors and ultimately sort of less code that you have to write, specifically less explicit cast. All right, so that's pretty much all I wanted to go over today. We will be doing more generics next time. We'll be creating our own. So generics are very easy to create. You saw the code for comparable. You're literally just putting in like a T or an E or a U or something in place of an actual type. And then you're just making sure you use that T or E or U in the appropriate places throughout your code. So it's actually really easy to do. Lab for this week, the week that you'll be watching this, we are going to have that first quiz, and PA3 will be due the following Friday after we have that first quiz. So that's all I have for you guys today. So we'll look at some more generics next time.